let's suppose that we have a vector space U, and let's suppose that V1 equal to U1 up to UK is a basis, and we have another vector space V, and V2 equal to V1 up to Vm is a basis, and let's suppose that we have another vector space with basis V3 equal to W1 Wn. Notice that the dimension of U is K, the dimension of V is M, and the dimension of W is N. And let's suppose that we have a linear transformation T from U to V, and we also have a linear transformation S from V to W. Then we can define a linear transformation from U to W, which is the composition of the two functions. And then an important theorem says that if I compute the matrix of T with respect to this basis, let me just say A is just the matrix of T with respect to bases 1 and 2. Remember, this is an n by k matrix. This is an n by k matrix. And if we compute the matrix B for this transformation, with respect to these two bases, let me write it down. Matrix of S with respect to the bases B2 and B3, and this is an n by m matrix. Then the matrix C, which is the matrix of this composition of functions, and let me write it down. Matrix of the composition with respect to the bases B1 and B3. Then this matrix is just the product of B with A. One way to remember the order of this is the following. Notice that this C is the matrix of the composition T composed with S. We write it like this because first adds T and then adds S. But the matrix of T is the matrix A, and the matrix of S is the matrix B. That means that C is B times A in this order. Let's do an example that illustrates this theorem. Let's suppose that U is just C2. Let's suppose that V is the polynomials of order 2 or less, and W is the polynomials of order 1 or less. Let's suppose that the transformation T takes these two complex numbers, A, B, into the polynomial A plus B x squared plus bx plus A. And let's suppose that the transformation S from here to here is just the transformation that takes a polynomial into its derivative. In particular, S takes ax squared plus bx plus c into 2ax plus b. Then in this case, the composition T composed with S, it will take an a comma b, it will take it into the polynomial a plus b x squared plus bx plus a, and then S will take this polynomial into the polynomial 2a plus b x plus b. Then this is the composition. Let me just erase this. And let's just say that AB goes to 2 times a plus b x plus b. Then let's compute the matrix A. To compute the matrix A, let us assume that the bases that we are using for U, the bases B1 are just the vectors 1, 0 and 0, 1. And in this case, I'm going to call to be consistent with that, even though this is E1 and E2, I'm just going to call it U1 and U2. For the vector space V, which is polynomials of order 2 or less, the basis that we're going to take is the canonical basis there, which is 1x and x squared. And I'm going to call this B1, B2, and B3. And for W, which is polynomials of degree 1 or less, I'm going to take the bases 1 and x. Just to be consistent with the notation, I'm going to call it W1, W2. Notice that in this particular case, K is 2, M is 3, and N is 2. Then, to compute the transformation of the matrix, to compute the matrix of the transformation T, we need to evaluate T of U1. T of U1, that means T of this vector, that means A equal 1, B equals 0, and that will go to the polynomial x squared plus 1. And then the first column of A, let me write it here, the first column of A is going to be the coordinates of this vector with respect to this basis. This vector is 1 times this vector plus 0 times this vector plus 1 times this vector. Then the coordinates are 1, 0, 1. Now, T of U2. T of U2 is T of this vector. That means A equals 0, B equal 1. And then we have, this is just x squared plus x. And the second column are the coordinates of this vector with respect to this basis. But this vector is just 0 times 1 plus 1 times x plus 1 times x squared. Then the weights are 0, 1, 1. Fine. And that's it, right? This is the matrix of this transformation. As I said before, this is a 3 by 2 matrix. 3 by 2 matrix. Let's see the matrix B. This is supposed to be a 2 by 3 matrix. And to compute that, I have to compute S in the first element of this basis, S of 1. But S is just the derivative. The derivative of 1 is 0. And how do I write 0 as a linear combination of these two? It's just 0, 0. Now the next one is S of x. S of x is 1. How do I write 1 as a linear combination of these two? It's 1 times this vector plus 0 times this vector. Then is 1, 0. And S of the third vector, x squared. And this is just 2x. How do I write 2x as a linear combination of these two? Is 0 times this vector plus 2 times this vector. This is the matrix B. Now, what is the matrix for the composition? The matrix for the composition, let's call it C. I need to evaluate the composition this is the composition. I need to evaluate the composition at U1. But U1 is the vector 1, 0. That means that A is 1, B is 0, and it will go to the polynomial 2 times x. What comes in here? The coordinates of this vector with respect to this basis. Remember that this composition is a transformation from U into W. Then, how do I write 2x as a linear combination of these two? Is 0 times this vector plus 2 times this vector. Then the weights are 0 and 2. Now, if I do the composition at U2, U2 is the vector 0, 1. And this 0, 1 means that A is 0, B is 1, and then it will go to the polynomial 2x plus 1. And how do I write 2x plus 1 as a linear combination of these two vectors? It's just 1 times this vector plus 2 times this vector, then it's 1 and 2. And the theorem says that this matrix should be the product of this with this. Let's see if that is true. If I do the product of B 0, 1, 0, 0, 0, 2 times A 1, 0, 0, 1, 1, 1, then I will get the matrix. When I multiply this by this is 0 plus 0 plus 0 is 0. When I multiply here, I get 0 plus 1 plus 0 is 1. And when I multiply this by this, I get 0 plus 0 plus 2 is 2. And when I multiply this, I get 0 plus 0 plus 2 is 2. Then that agrees. That checks this theorem. If we consider a vector space and then the identity function which takes a vector v into v has the property that the representation of this transformation with respect to any basis, if we pick the same basis here and there, then the representation is going to be the identity matrix. Then this is if basis 1 equal to basis 2. Notice that we don't need to pick the same basis for the domain and the codomain, but if we do, then the matrix that we get is the identity matrix. Then let's suppose that we have only one vector space, and let's suppose that we are only considering one basis for the domain and the codomain. And let's suppose that we have a transformation T from B to B, and then let's suppose that this transformation T is injective and is surjective. That means that it has an inverse. Then if it has an inverse, let's denote that by T inverse, and it goes from B. And then when we compute the representation of this transformation, if we call it A, and we compute this matrix B, the representation of this transformation, then I know that the composition of the T with T inverse by definition is just the identity, and therefore we have that A times B is just the identity matrix. Then essentially what I'm pointing out is that we have a linear transformation, and that linear transformation has an inverse. Then the representation of the inverse is just the inverse of this matrix. Then let me write it down. If we are using the same basis for B, we just put as domain and codomain, then the matrix that represents T inverse, in case that inverse exists, is the inverse of the matrix that represents T.